Hey guys, so for this video I'm going to be doing the exam that we did in class today, the 2012 exam. I'm just going to go over all the things, even though the stuff that we covered already, just so you guys can have a reference material. Alright, so for the first one, we want to find the longest chain, and so I'm just going to eyeball it and quickly see if I can figure out where I have the longest chain. So just gonna do this. 1, 2, 3, 4, 5, 6, 7, 8. Okay. 1, 2, 3, 4, 5, 6, 7. Okay. Let's see. One. What have I done already? Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 that way. And then I have, let's see. I also have 1, 2, 3, 4, 5, 6, 7, 8 that way. And I also have, let's see, 1, 2, 3, 4. I also have it this way, so okay. A lot of annoying paths. But it's always good to see if you have any similar number of paths so you can compare them. Alright, so for the green path that I just did, I have how many groups? So I have 1 on 2, and then I have 4 on 5, and then I have 1 on 6. Okay, and then for the red path, I have 1 on 2, I have 1 on 5, I have 1 on 6, and I have 1 on 7. And then for the black path, I have 1 on 2, 1 on 5, and then 1 on 6. Alright, so red path wins. These are all 8 carbons long, so the red path is the one that I'm going to choose. So I'm going to choose a red path over here. So let's just circle the stuff that's on the red path. So I have this group on the red path. I have this group on the red path. I have this group, and I also have this group. Okay. So now let's number these substituents. So I have on. Let's do the hardest one first. So I have on this one over here, coming off of this carbon, is a 1, 2, 3, 1, 2, 3. So it's 3 either way. Okay, so either way I have 3. And so what this could be called, actually before I start naming it, I need to see if I have a faster way to name it from the other direction. So I need to quickly see if, because right now I went from left to right, I mean, I went from right to left, so I went in this direction. Now I see on this direction, what do I have? If I go in from over here to over here, I have 1, 2, actually I should probably do it another color. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so if I do it in this direction, my numbering is going to be 2, 3, 2, 3, 4, and then 7. Okay, so right away the blue direction is the one I want to go in. Okay, so I need to erase probably all this stuff. All right, so 1, 2, 3, 4, 5, 6, 7, 8. All right, and I have this group, this group, this group, and I have this group. Okay, so this group right here is going to be called, well, let's name our methyl groups, right? So I have 2, 3, 7, dash trimethyl. Okay, and then on 4, what do I have? I have off of 4, I have a 1, 2, 3, right? So this is an ethyl, and then this is a, right? And this is a propyl, and this is an ethyl. So the propyl is going to be the parent chain for the substituent, and the ethyl group is going to be coming off. So I have 4, and it's coming off of 1, 2, 3. So it's 4, 1 ethyl propyl. Okay, so our full name for this one is going to be. Alright, so now what comes first? The M in methyl or the E in ethyl? So it's going to be the E in ethyl. So I have 4, 1 ethyl propyl, right? And then dash 2, 3, 7 trimethyl, right? And then what is our parent? Octane, right? Alright, and then for this one, let's do it quickly. Alright, what does this group look like? So it's coming off like this. Let's say this is the parent right here. I have this carbon right here, attached to a carbon right here, and this carbon has like that, right? So it's 1, 2, 3, 4, right? So 1, 2, and then 2 of these groups. And then over here, this is the isopropyl group. And like we did in class, they're completely opposite. So this is 1, 2, 3, 4, and if I, go any other way, it's gonna be the same thing. So what I really have to choose between is, am I gonna make this one number 1, or am I gonna make this one number 1? That's the question. So I choose by first I need to name it. So this is isopropyl. Okay. And then this one over here is a 1, 2, 3, 4, so that's a butyl. And so this one over here is a, right, it's a 2 ethyl, butyl, okay? So A, B, C, D, E, F, G, H, I, so E is before I. So I'm going to be naming this, right? Well, first thing first, right? So this is going to be 1, 2, 3, 4, okay? And then I need to, whenever you have rings, right? So if they give you the, the wedges or dashes, right? You have to be careful of their stereochemistry. So when you have two groups, you have to be careful of their stereochemistry. So cis or trans. So over here, Renee did an easy way. One is going down, one is going up. So that's trans. But another way you could look at it is, I have on a ring, right? I have two groups that are equatorial, and they're exactly opposite each other. So one is on this position over here, the other one's on this position here. So if I say that this light wedge is equatorial, for it to be all the way down here and also be equatorial, it has to be the opposite. It has to be a dark wedge, right? And that's something you can just memorize. So when they're opposite of each other on the opposite sides of the ring, the different color dash or wedge are going to be the same position, equatorial or axial, okay? And you can check this by filling in the rest, but this is just one thing you can memorize. So this is trans. Right, need to hurry up here. So I have trans, right? And then I have on position number 1, I have 2 ethyl butyl. And then on position 4, I have isopropyl cyclohexane. Okay. All right, so I have this. And then now let's do this molecule. So it's usually very clear when a ring is a substituent by just like how it looks like on the drawing. So these are pretty clearly coming off of this chain, right? And we can just now number the chain. So 1, 2, 3, 4, 5, 6, 7. Okay, and it's 7-membered ring. I mean 7 long, right? And then in this direction, it's 1, 2, 3. This is 4. This is 5. This is 6. This is 7. So in the red direction, right? So going this way, I have on 3, right? It's gonna be may not be the same actually. So I have 3, 4, and in the black direction, I have it on 4, 5. Right. So right away, red direction is the winner. Okay, so now I need to name these. So this is just cyclohexyl and this is cyclobutyl. Okay, so sorry, that's not legible, but you'll see it in the full name. So whenever you have something as a substituent, just drop the ANE and add YL. So over here I said 3, so 3, right? 3 cyclo, and well now I have to actually what's alphabetically first. So what's alphabetically first? Cyclobutyl or cyclohexyl? So cyclo counts alphabetically. So now I'm comparing the H and the B. So obviously the B comes first. So the B is on 4 cyclo, and then 3 cyclohexyl, and then this is heptane. All right, and now let's look at number 5. So number 5 is one of the ones she gives you the name written out, and you have to draw it. So I have 5-sec-butyl 4-ethyl neopentyl decane. So the easiest thing to first do is just draw the parent. That's how you start. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and now I'm just going to add my group. So 5-sec-butyl. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5-sec-butyl. So sec-butyl looks like this, right? So 1, and I have a group coming off of it. And then butyl is 4 groups. I already have 2, so add 2 more. So 1, 2, 3, 4. Okay, that's sec-butyl. And then now I need to add the 4-ethyl. So 1, 2, so it's ethyl. And then 6-neopentyl. So that's a 5-member one. So a neopentyl just looks like this. So I have a carbon, and then I have a carbon, and then I just add this. Okay, it's basically like a T-butyl at the end. All right, so this will be your answer. Okay, now let's moving on. Right. Let's see. All right, so draw a proper Lewis structure for the condensed formula below. Be sure show all lone pairs and formal charges. Okay, so the way I would do this is, well, you can do it. You can count all your electrons. You can do all that biz, but this looks like a pretty like straight out written out formula to me. And what I mean by that, it's like it kind of gives you some hints that what is connected to what, and that'll help you draw out the whole molecule. The rest is going to help you to check, if you put all the right number of electrons and all that stuff. So let's just note it's it's neutral, and we can count the number of electrons over here later. I'm just going to give my proposed structure. So we have, I'm going to put the O in the middle, and it says 2 CH3s coming off of it. So okay. All right, and this is connected to a aluminum, and this is connected to 3 chlorines. All right, and then I'm going to give this oxygen a lone pair because it needs a full octet. All right, and now each one of these is going to get a full 3 lone pairs. Okay, now let's count the number of electrons. So I have each one of these CH3 groups is a total of 7 electrons. So 4 plus 7, 7 times 2, that's 14 for this. The oxygen is going to be 6. The chlorine is 7 times 3, so that's 21. And then the aluminum, let me just check. Okay, so aluminum is going to contribute 3. Okay, because aluminum is right here, so it's in this column. All right, so aluminum is 3, so this is 14 plus 6 is 20, 23. And then 21 plus 23, that's 40, it's 44. Okay. Now let's check. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44. Okay. And now I need to add my charges, right? So I have an oxygen with three bonds and one lone pair. So this oxygen is positive. And we said aluminum has a valence electron number of 3 and has 4 bonds. So 3 minus 4, this is -1. So this is negative. Okay. And this is your Lewis structure. All right, moving on. Place the compounds below in order of increasing melting point. So we said melting point. All right, I'm just going to type this out. All right. Increases with mass and branching. Boiling point increases with mass decreases. Ugh, branching. Okay. All right, so here in class I already counted to make sure that they all had the same number of carbons. So that's the first thing you should do. Make sure that all the molecules that she's making you compare have the same number. So let's say like you had one that had 6 carbons, another one that had 7 carbons, but the one with 6 carbons is way more branching. But the one with 7 carbons would still be more, okay? So she's going to make it very comparable. She's going to give all of them the same number of carbons usually, but just always count and make sure that they all have the same. All right, so they all have the same here. I believe they all have 7. So the one with the most branching is going to be the highest. This is the second most, and then this is the least. All right, let's place the compounds in order of increasing solubility. So we said H2O looks like this, right? It's polar, and it also performs hydrogen bonding. So I'm looking for what hydrogen bonds, and I'm looking for anything that's polar. Obviously, hydrogen bonding is stronger than polarity. I'm going to pull up the table really quick. Right, so this is a quick table that I just pulled up that gives some basic ordering of types of interactions. So covalent bonds obviously strongest, and I believe you might have ionic around here, but you might have to find something more accurate. And then you have hydrogen bonding, dipole-dipole, so this is like polar interactions. Then you have London dispersions, which are just nonpolar molecules interacting by just their electrons orbiting around, and then you suddenly have a very, very slight and quick dipole moment that allows the molecules to interact. So this is the weakest, this is the strongest, and obviously hydrogen bonding is up here. All right, so let's look at our sketchpad. So I have oxygen, hydrogen, hydrogen bonding, and so I want the thing that's most similar to that. So the thing that's most similar to that is this OH right here. So this is going to be 3. And then I have another hydrogen bonding here with nitrogen. So my 3 hydrogen bonding atoms are fluorine, oxygen, and nitrogen. Okay, so this is the next hydrogen bonding thing, which is stronger than polar interaction. And then finally I have this ether right here. And this is gonna, you don't need to know what that is, just that's the name of it. And this is gonna be polar, right? Because the oxygen is gonna pull in the direction towards itself and make everything else partially positive, and this is gonna be 1. Okay, moving on. All right, so let's look at this. So I did this one already in class, and I started with this direction. I could also start in this direction, but you just kind of have to eyeball it and really, you might get unlucky and you might start in a direction that's not as convenient, but just keep working your way through it and try to get the structure where you obviously have this nitrogen able to contribute into the ring, because that's what ultimately we want. That's what she's like teasing you with over here. So I'm just gonna keep doing this. All right, I'm just gonna skip ahead and show all the structures, and you'll see it then. Alright, so here's all the structures. So I just kept resonating this up here, and then this up here, and every time I showed the positive charges, and I eventually started writing nitrogen like this because I was too lazy to keep drawing out the CH3 There's just two CH3s coming off of it, and keep resonating it, keep resonating it, and as many times as you can. And finally, I got the positive charge over here, and all we're gonna do is move this lone pair in right here, okay? And I'm gonna get my structure that I want, right? And I'm so desperately trying to get the structure because, right? Because it's the only one where I have a full octet where the pause charge is. So all the others, I haven't had octets on them yet. And so this is the only one where I have the pause charge moved to a location where I have an octet. So all these were not octet. And so this is going to be our major. All right. Now place the compounds in order of increasing acidity. So now I just deprotonate every single one. So this is S minus. This is O minus. And then this is a very easy one. And this is N minus. Okay, so now I'm just comparing atoms. So what's better, oxygen or nitrogen with the negative charge? Oxygen, right? And nitrogen is the worst. Okay, so this is 1, this is 2, this is 3, right? What's better, sulfur or oxygen? Sulfur is in the same column as oxygen, so I have carbon, nitrogen, oxygen, and then sulfur. This is more electronegative, this is heavier. So when they're in the same row, I'm comparing the one that's going to be more acidic is going to be the one that's more electronegative. So oxygen is more acidic than nitrogen. But when they're in the same column, the one that's heavier is going to be more acidic. So sulfur, the molecule with sulfur is going to be more acidic than the one with oxygen. And as you can see, she keeps one thing constant. So all of them have the same amount of resonance with that carbonyl. The carbonyl is just the structure with the double bond O. That's what's called a carbonyl. And all of them can resonate into this and pull it out, okay? So that's that one. All right. And now let's keep going. All right, draw all the structural isomers resulting from the monobromination of blah, blah, blah. All right, you'll be penalized for duplicate structures. So it's very easy to draw duplicate structures. So earlier today, I messed up and it's very easy to fall for this because look how she draws it. All right, she draws these closer together than she draws this one over here. But in reality, you have to notice that these are all methyl groups coming off of this one carbon. So this is A. This is also, I'll draw B. This is A, and this is A. Okay? And Renee just wanted me to say this is B because, you know, this is another carbon, but it's not going to be one that we can use because it doesn't have any hydrogens on it, right? Where it's necessary that we have hydrogens. This is C. This is D. This is E. This is F. This is F. All right. So I have how many environments? I have 1, 2, 3, 4, 5. Okay, 5 unique environments. So I'm going to draw this quickly. All right, so the first one, I'm going to attach a bromine right there. And then for the next one, I'm going to attach a bromine. Oops. All right, so for the next one, I have to attach a, so there's these 3, right? And then, okay. And then I think I did that right. 1, 2, blah, 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 blah. All right, attach one right here. Right, and then, oof. Okay, and then, I need to attach one right here. Okay. I need to attach one right here. And then I need to attach one right here. Looks looks really ugly, but I think you all get the point. Okay, so these are my 5 structures. All right. And this is more difficult when she just gives you a formula and you have to like draw all the different isomers that the formula has. That's more annoying, okay? But usually she does the monobromination one because it's too many things to put on an exam if she doesn't do that. All right. So now let's do this one. So it's just hybridization. So she's saying write the hybridization for each atom indicated in the box. So in the box to the right, whether it's sp1, sp2, sp3, whatever. So I need to consider resonance. So I have lone pairs and I have this charge. So this charge is only going to be able to come into here. Okay, and go up over here. All right. And anything else? No, not really. We don't have anything else. So my resonance occurs right here. So carbon, I'm just going to do carbon A as well. So I have 3 things on it, 4 things. So this is sp3. Actually, this might be better with the typing thing. Never mind. All right, sp3. All right, this one right here has 1, 2 groups. So this is sp. Right? This carbon is here is also sp. This carbon right here is 1, 2, 3. So this is sp2. Right? This carbon right here. So I resonate the electrons in, right? So whenever you're doing this, you always consider the lowest hybridization. This one has 2 hybridizations. Before I move the electrons in, right, it looks like this. After I do it, it looks like this. So in the beginning, it has 1, 2, 3, 4 groups. After resonance, it has 1, 2, 3 groups. So the 3 group one is the one I'm choosing. And that's going to be sp2 because it's lower hybridization. Carbon C, this is 2 hydrogens, 2 bonds. This is sp3. Right? Carbon D, so this is a double bond. So I know it's going to be sp2. This nitrogen has 1 group, 2 groups, 3 groups. So this is sp2. All right? So that's that. Okay, what is the CDNE bond angle? So what you do for this is just you look at the bond angle of the middle one. So CD is right here, right? And so this is what I say, this is sp2. Okay, what this actually is, sp2 is, I believe, 120. Okay, so this is what you write actually. Okay, the 120, the angle. The sigma bond between the atoms labeled A and B is formed by the overlap of what types of orbitals, right? So between A and B. So this is sp3, this is sp. So sp3, sp, okay? And just look at the answer, this is what you write. So sp3 and sp 120, right? And I said sp, sp2, sp2, sp, sp2, sp2. Right, so these are the correct answers. And this person has also 5 structures over here. And what they did, they also calculated the unsaturation number, but this was actually unnecessary to do for this problem. Okay, unsaturation number is useful when she gives you the formula and you have to write out all the isomers. All right, let's keep going. Almost done. All right. It's gonna start getting a little bit harder now. Right, viewing the molecule along the C3-C4 bond, construct the Newman projection of the most stable conformation of 3,4-dimethylheptane. Okay, so this is 1, this is 2, this is 3, this is 4. All right, and now I found my bond, and I need to look at the 3 groups coming off of each one of this one and this one. So I have 1 group, 2 group, and the hydrogen that's invisible. And then I have a hydrogen that's also invisible here. And then I have 1 group, 2 group. Okay, most stable. So that means my Newman projection is going to look like this. Right? So draw that more nicely. So it's going to look like this. All of them opposite to each other, right? Nothing touching, no overlapping. So the front side is this over here. So right away, let's find my biggest group. My biggest group is this ethyl group right here. So I'm going to put my ethyl group. So this is like this. So this is one carbon, this is two carbon, that's ethyl. And then I'm going to put opposite to it this biggest group back here. So this is a 1, 2, 3. This is a propyl group. So 1, 2, 3. Okay, so these are opposite to each other now. And then now all that's left is to draw the remaining ones opposite to each other. So you can put the hydrogens over here, the hydrogens over here, and then I have a methyl group over here and a methyl group over here, and we're done. Okay, so this is the answer. All right, and let's just check real quick. All right, so they put oh, it says least stable over here. That's weird. Well, this is most stable. If we're going to draw the least stable, which I guess this person made a typo, we would do this, and then it's very deformed. And then I would draw the biggest group on top of each other. So my ethyl group now, and then my, my propyl group. So 1, 2, 3 next to each other, and then my methyl groups next to each other, and then my hydrogens next to each other. This would be least stable. This is most stable. This is least. Okay, eclipsed. And let's just check what they did. So yep, right? Those are that group. This is the CH3s, the hydrogen. So it looks like mine. Now let's do this problem. Draw the more stable chair conformation for each of the substituted cyclohexanes shown below. So she gives you 2 of them, and then at the end, she says which one of these 2 is more stable than the other, okay? Which is something that you can compare. They also have the same groups, they're just different wedges and dashes, so it's very comparable. All right, so what does this look like? This group over here is, right, it's the T-butyl group. So this is how it would look like off of a bond. So it's that big bulky one. This is CH3, this is just a CH2, CH3, okay? So this is the biggest one. So I'm gonna circle biggest, right? And each time I'm gonna make this biggest one, right? And I don't have any other big ones. I mean, these are also big, but this is the biggest compared to all of them. Maybe you have more of these T-butyl groups, and at that point you would have to try to get as many of the T-butyl groups on equatorial. But I only have one, so this is the only thing I care about. I'm gonna make this equatorial. I'm making this equatorial. I'm doing this the fast way, okay? My way. So, I mean, it's not really my way, but I mean, it's the way I always do it. And so, equatorial, so that means light wedge over here is equatorial. I mean, is axial, right? And then that means light wedge over here is equatorial. And that means light wedge over here is axial, right? And then now that this is axial, right, light wedge over here is equatorial, and the dark wedge is now axial, right? So I have dark wedge on axial, this one on axial, and then this is on equatorial, okay? So what does my chair look like? All right, so I'm gonna number this. Now it's not very clean, but I'm gonna number this 1, 2, 3, 4. Okay, so I'm gonna name it. I'm going clockwise. So 1, 2, 3, 4. Okay, so on 1 I have my T-butyl group on equatorial. So amazing. And then on 2 nothing, and then on 3 I have this on axial. So axial goes up like this. So I just have a CH3 group. Right, and draw the hydrogen out in equatorial. And then on 4, I have this also in axial, so I have this like that. Bam. Okay, so this is what I have. I have this on equatorial, and these 2 on axial. So I have 2 axial and 1 equatorial. Now over here, Let me draw my chair. Okay, and one easy trick, right? When I am on the other side of the molecule, right? Dash and wedges that are opposite, so these are opposite, that means this is also going to be equatorial. If you saw over here, I had dash, and they were opposite, and they were opposite, equatorial and axial. But when you have dash, and then on the opposite side you have a wedge, or whatever, they're going to be the same position, okay? So that's just an easy trick. And then whenever you have 1 over, then you're going to have everything flipped. And then when you have 2 over, then you're going to have restored what you initially had. So over here I have, these are just the faster tricks than having to draw every single one. So dash is equatorial here, this is axial. So 2 over, this is going to be axial, okay? And then over here, this is equatorial. So I've already figured it out. So my thing over here, this is 1, 2, 3, 4, okay? And so now 1, 2, 3, 4. So 1, I have my T-butyl group, all right? 3, I have this on axial, right? Still on axial. And same thing as before too. So this is CH3 group. But now on 4, I have this group on equatorial, okay? So this is on equatorial now. And so now on this one, I have these 2 groups on equatorial and this one on axial. Whereas before I had 2 groups on axial and only 1 group on equatorial. And this is comparable to this degree because both the biggest groups on equatorial on both of these chairs. So they're very comparable, right? So all I have to compare to figure out which one's better, I drew up both of the most stable ones. Okay, these are both the most stable ones. Now to compare which one's more stable, A or B, after I see that the biggest groups are both equatorial on both of them, right? Now I just need to see if I have anything better. So over here I have this on equatorial, but this is on axial, and both of these are on axial. So this one is clearly better. So B is better, okay? And we can just check really quick. B is better, all right? And now let's finish up. Let's see. All right. And so now I already did this one actually in a past video. I took an example from this one, but let's just do it again. So I have to show the propagation steps. So the propagation steps is, so I said initiation, and put an I for initiation, is simply when I have the BR, light comes, bam, and then it breaks the bond, right? And I get 2, you don't really have to put the 2, but the main thing is that I'm forming BR radicals. So the propagation step is part A, so the step A, where I have this thing, and I have a hydrogen drawn out, plus BR radical, and it's going to come, all right, and a radical goes right there. Okay, plus HBr is formed. Don't forget to write that out. And then step B, this guy, plus, right, BR2, it's going to do this, right? And the way you know that you're not reacting this with just a BR radical is because this is called propagation, right? So we're going to see real soon why this is called propagation, right? So what's created? I made this plus another BR radical. And Br radical is what allows this system to keep going, right? I need this guy to come again and react to another one of these. So if you don't make a Br radical by the end of your part B of the second step of your propagation part, then you know you did this wrong. That's why we don't just react this with the Br radical. That's why reacting this right here with the Br radical is considered a termination, because it doesn't keep the reaction going. It just stops, right? So I just stopped. So consider the termination steps. Provide a structure for a possible side product. There's the side product where this actually reacts with this, right? There is a side product where the Br reacts with another Br radical, and then there's another side product that the best one to show is where this reacts with itself. Okay, so when this reacts with itself, this forms a bond with another one of itself. Okay, that's what we want to show, right? That's what we want to show. All right, given the bond association energies below, calculate the overall delta H for the reaction in the box provided. Okay. Okay, so what is this doing? So what I'm doing is I'm doing the calculation of the bonds that were broken minus the bonds formed. So what bonds were broken? I broke a, I'll put broke. I broke a BR bond, and I broke a, what I said was a secondary hydrogen, a secondary carbon's hydrogen bond. Okay, so I broke these, and I know secondary just means the carbon that the hydrogen is coming off of, or whatever the carbon that we're looking at, is attached to two other carbons. That's all that secondary means. Okay, so this is secondary carbon right here. This carbon is a secondary carbon. And then I formed, right? I formed a secondary carbon bromine bond, and I also formed an HBr bond. Okay, so I'm doing these energies minus these energies. So let's just look over here. So I look for those values. So the Br2 bond is 46, right? So this is 46, and let's see, a secondary carbon. So it's right here. CH is 95, and a bond to a bromine secondary 95, and this is gonna be right here 68. Okay, this is right here, this is 68, and then the HBr, right? So bonds HX, so this is X represents a halogen, so it's right here, HBr 88. Okay, so what I have is 95 plus 46 minus 68 plus 88, okay, equals whatever the answer is, negative 15. Okay, negative 15 kilocals per mole. You have to write the units, or else you'll get points off, right? Kilocals per mole, right? And what is this? This is an exothermic reaction, right? Because it's negative, right? And because it's negative, our products are going to be favored. So I'll put products. Cool, right? And so that's it. I hope this was helpful for you guys, and let me know if you have any other questions about this stuff. See ya.